Welcome to this section about neutron porosity tools. Today, we'll explore their applications, logging conditions, and the principle of operation. We'll also see how the borehole conditions affect neutron porosity tools and why they generally use dual detectors, ending with a discussion on equivalent porosity. Let's begin. The primary objective of a neutron porosity tool is to determine formation porosity and assist in lithology identification. Additionally, they can also aid in the shale volume determination and gas bearing formation identification when combined with density or sonic porosity data. Certainly, logging conditions significantly impact the accuracy of a neutron porosity measurements. Factors such as borehole size, salinity, and the detector standoff, which is any physical separation between a detector and the formation. Well, all these factors must be considered to ensure reliable data, but in general terms, neutron porosity tools can be used on freshwater-based mud, saltwater-based mud, oil-based mud, and even on case holes. Now, let's get into the details of the principle of operation. It turns out that neutron porosity tools don't measure porosity directly. Instead, they measure the abundance of low-energy neutrons in a formation. You might be wondering, and how is that related with porosity? Well, here's a brief description. First, consider the process of neutron emission. The tool uses a chemical radioactive source to emit high-energy neutrons into the formation. Then, these neutrons collide with atomic nuclei in the formation. With each collision, they lose energy, a process called thermalization. Then a key player comes into place, hydrogen. Hydrogen atoms are particularly effective at slowing down neutrons because they have nearly the same mass. This is crucial because hydrogen is mainly present in fluids, oil, water, gas, that occupy pore spaces in a formation. As the neutrons lose energy and reach thermal levels, they can be detected by the tool's sensors. By the way, the tool typically has two detectors at different distances from the source to improve accuracy. And here is the relationship. The number of detected low-energy neutrons is inversely related to the hydrogen content, which means higher hydrogen content, indicating higher fluid content, and thus higher porosity, results in fewer neutrons reaching the detectors. Then, by calibrating the tool responses in known porosity values, we can interpret the measurements to estimate formation porosity. Again, in summary, neutron porosity tools emit high-energy neutrons, but measure the resulting low-energy neutrons after interaction with the formation, and interpret this data to estimate hydrogen content. Since hydrogen is primarily found in pore fluid, this measurement serves as an indicator for formation porosity, allowing us to indirectly assess the potential fluid holding capacity of the rock. The neutron source in porosity tools typically involves a chemical source, such as americium, beryllium, or californium-252. These sources emit high-energy neutrons that interact with the surrounding formation. Nuclear logging tools typically use two detectors, a short space SS detector close to their radioactive source and a long space LS detector further away. The ratio of their readings is called SS-LS ratio. As porosity increases, this ratio also increases. This is because more porous rocks contain more hydrogen, which slows down neutrons more effectively. This leads to a greater difference between the SS and LS detector readings. Different rock types affect SS-LS ratio differently, which also helps in determining lithology. For instance, dolomite slows neutrons efficiently, resulting in a higher SS-LS ratio than limestone, and quartz sandstone is less efficient at slowing down neutrons, leading to a lower ratio than limestones. We previously mentioned that the chemical source emit high-energy neutrons and that detectors measure thermal neutrons. To better understand this, here we can see the energy levels of neutrons. Since energy levels are expressed in a unit called electron volt, EV, let's define it. An electron volt is a unit of energy equal to the kinetic energy acquired by an electron passing through a potential difference of 1 volt. For example, a neutron with an energy of 1 mega electron volt would have the same striking power as an electron accelerated through a 1 million volt potential. Let's explore how neutrons lose energy in the formation. The primary mechanism is through elastic collisions with atomic nuclei, similar to billiard balls colliding. Hydrogen can cause a neutron to lose about 50% of its energy in a single hit, while other elements can also slow neutrons. They're not nearly as effective as hydrogen. To better understand the neutron slowing process, we need to introduce two important concepts. First, the slowing down cross-section, shown in the green column of the table. This measures how efficiently an element can slow down fast neutrons to a detectable thermal level. The second key concept is capture cross-section, shown in red in the column. Once a neutron is slowed to thermal level, it randomly moves around until it's captured by a nucleus. The capture cross-section represents the likelihood of a nucleus capturing a thermal neutron. Understanding these two concepts help us interpret and account for the effect of different elements in the formation. We mentioned that a few corrections should be applied to neutron porosity tools measurements. Let's begin by analyzing borehole size. Borehole size also has an influence on count rates. The larger the hole size, the larger the volume of borehole fluid and therefore hydrogen that neutrons must pass through, resulting in lower count rates. The effect of hole size on the count rate is bigger in situations where the borehole is filled with a high salinity drilling fluid. To understand how salinity affects neutron porosity tools measurements, consider that an increase in the salinity of the borehole fluid results in two competing effects that influence the count rate measured by a thermal neutron detector. These effects are: first, added sodium chloride increases the thermal neutron capture cross-section of the borehole fluid, and second, added sodium chloride decreases the hydrogen concentration within the borehole fluid. The second of these two competing effects predominates, resulting in count rates that are significantly influenced by borehole salinity. Fast neutrons emitted from the source interact immediately with the nuclei of atoms present in the borehole fluid, because these neutrons are not at thermal energy levels so close to their source. They are not greatly influenced by the capture properties of the borehole fluid. They are, however, significantly affected by the decreasing hydrogen concentration as borehole salinity increases. Overall, an increase in borehole salinity results in an increase in the count rates. Lastly, detector standoff, the physical separation between a detector and formation, significantly impacts count rates in nuclear logging. While decentralizers minimize standoff effects, other factors remain. In open holes, mod K and irregular conditions contributes to standoff, with the impact depending on the slowing down and capture properties of the intervening material. In case holes, casing and cement sheet create a standoff with their properties and thickness determining the effect on count rates. Despite decentralization, residual standoff effect requires real-time or post-process correction. So far, we've learned that the tool measures a ratio of thermal neutrons captured by the detectors, but this ratio by itself doesn't tell us much about the formation, right? What we really want to know is the porosity. So how do we get from this ratio to porosity? That's where calibration comes in. Service companies use a practical calibration method. They start with a standard tool that's calibrated in the API pit. This tool measures the SS-LS ratio in a simpler calibration, usually a water tank, which then becomes the reference for all other tools. During shop calibration, each Neutron tool is calibrated in this water tank. A sensitivity factor is calculated to match its ratio with the standard of tool ratio, ensuring consistent readings across all tools. For field operations, the verifier check block or snow block is used. This portable reference is checked before and after each logging to run and make the tool's calibration stay stable. The Neutron tool's SS-LS ratio is initially calibrated assuming a type of rock matrix and a type of fluid. For example, freshwater filled limestone. However, this ratio changes with different lithologies and fluids. Before logging, the user, in this case, the field professional from the service company, selects the matrix or neutron lithology that best represents the formation. If the assumed lithology is incorrect, the neutron porosity will be incorrect, but it can be recalculated later using the correct lithology to ensure accurate results. Well, we've covered a lot of ground in this module, from the basic principles and applications of neutron porosity tools to the detailed factors affecting their measurements and the importance of calibration. Thank you for joining this session of neutron porosity tools.